tell you some. I will tell you some brief idea to get brief idea. Okay, this is a state space. State space model means we need to deal with system MIMO, multiple input, multiple output system. As I think we are asked to, we are given, we can be given some equation like x1 equal x2 plus x3 like plus ut, like some system of equations, and we need to convert it to a matrix form, like question matrix form. We did some example in our lectures. We did some example. We need to convert this system of equation into matrix form. We have multiple input, multiple output. We can say this system, if this is the plant, U is the input and X is the output. We can say this equation, plant system equation. System equation, let's X dot equal A plus xt B times ut. Those are matrix and those are vectors. B also can be vector. So we need to convert this system into this format, matrix format. Then we can write A matrix format and B. This can be a problem. I think this sort of a question can be in our paper. So then we can write, yes, this is ut is the system input. Xt is the output, but this is the system relationship. Then we need to find an open loop system, the stability. If we want to find open loop stability, means we connect plant directly. Here we supply ut or input and we have the xt output. So we control some part the output. We directly, if we use directly this system, we need to know the system is stable or unstable for this ut input. So we can use characteristic equation for characteristic equation. Open loop condition characteristic equation is given by Si minus A. So 0. Normal we know for this is the characteristic equation for matrix A. We know how to find eigenvalue using this root. Okay. Solution for this equation is represent eigenvalue. In theory, we know, so there are some theory parts in numerical method also about this eigenvalue. They should be, I don't exactly remember what are they, but there are some relationship in between the convergence of the some method of Newton-Raphson or some method with this eigenvalue, the polarity of these eigenvalue. So like we can use this characteristic equation to find eigenvalue. So in S domain, we use Laplace domain. Laplace domain, we can Laplace plane real part and imaginary part, we can represent it. And if you want to, this system should, when the system is stable, the poles eigenvalues should be in here. Yeah. Means real part should be negative. Real part of that is should be negative to stable the system. And if purely purely imaginary variable, if this is purely imaginary, the imaginary value, then they can't be repeat. So with this sort of similar relationship, we need to remember those things, and also how to using the characteristic equation and finding eigenvalue, we know how to present stability, how to tell stability if it is stable or whether it is unstable. Or we can use characteristic equation to have root theory, develop root theory. We can use root theory. Root theory, we know how to develop this, this, this how to develop this array, and we can tell stability using the first column will be greater than or equal to 0. Okay, so we can use this method. This is open loop transformation. We know we need to know strings. There can be question regarding this stuff. Another one is full state feedback control. Feedback control. The diagram. We need to know this diagram. This is the plant. This is U. This is X output, and this is the feedback part multiplied by K. In the system, we present X dot T equal AXT plus B UT. The UT is the input. We know how to control. When we develop this full state feedback controller, then we need to know how to tell the instability. The important thing is whether the system, open loop system is unstable, sometimes we can make full state feedback control whole system as stable. So now we need to tell stability. We need another characteristic equation. This what U equal K times xt plus R. This is U. K times xt plus R. We can say R equal 0. Then ut equal kxt by us equal kx is necessary. So we can use this relationship to get know how to find characteristic equation Si minus A. A minus B2. Make the determinant of this part equal to 0. This is now characteristic equation. No, why R is equal? They actually select all this part with the reference. We can make it 0. We can make R is the reference, so we can choose another value. For this finding the stability, we can say R equals 0. We simplify those equation to this format. U is equal k plus k times xx. This is our characteristic equation, new one. Then we can find eigenvalue. Uh, Eigenvalue. And we can say the real part should be negative, and if it's a purely imaginary value, they can't be. We can find whether this is stable or unstable. But here we have k value. K is this all part. This is number here in complex number. I matrix, A matrix, B matrix, and K is also matrix, column matrix. So, eigenvalue, or we can use Routh array. We can use Routh array to find the stability. We can, so if here stability depend on k value. It's k1, k2. This sort of a vector. We call it row vector. Eigenvalue depend on this k1 and k2 value. So k1, k2, k3. The system is somewhat big. So we can now we can change stability. Change stability using, we can select k so that the system is stable. To make sure the system is stable. Right? There is an example, and I write the final value. Is I minus a minus b k determinant equal s square plus k1 minus 3 s plus 1 minus 2k1 plus k2 equals 0. So we can develop Routh array based on this characteristic equation. Routh array like k1 minus 3 and 2 is 1, 0. This is 1 minus 2k plus k2. Okay. Okay. So we can choose those values to be greater than or equal to 0. Greater than 0, not equal. Greater than 0. So then we can decide k and k2 based on this inequality. So we can choose k, we can choose s equal minus 5 and minus 6. Those are eigenvalues. Two eigenvalues. We select eigenvalues to be minus 5 and minus 6. Then based on that, we can find k1 and k2. If we design our k or feedback using this knowledge, with this value, we can make sure the system is stable. This is one method. Okay. Sometimes we can't do it. Sometimes there can be solution like there can be some solution like this characteristic equation s1 minus s minus 1 minus plus k times s minus 2 equals 0. This eigenvalue not dependent on k, independent of k. So we can't control that eigenvalue. Pole actually. Pole. Eigenvalue pole. Name it as pole. We can't control it. That part root equal s equal to. S equal to means it's a greater than number 0, positive number. Positive number means the system is unstable. So it means we can't make the system stable using controller. Right? System is unstable system, open loop. In open loop state, it's unstable, and it's a feedback or closed loop state. It's also unstable. We can't make the system to be stable. Right? It should be positive plus one, plus two. The eigenvalue should be negative, and negative, that would be stable. We can make sure this part to be negative, this part to be positive. Okay, this part minus one plus k1 to be greater than 0 to make sure this system to be stable. Because 0 is equal 1 minus k1. This should be negative. Same relationship. Otherwise, we can use this. If we need, we we can make system and check stability. Or otherwise, we can find stability or controllability. Controllability. Controllability means we can control system using controller. Or we can make sure the system to be stable using controller. That's sort of it. Okay. Controllability. Using controllability matrix, yes, MC. MC is given as A, AB, AB square. This is first row, this is second row, column, second column, third column, because M should be square matrix. So square, not the square, this is rectangular matrix. Sorry. Yeah, this should be rectangular. We can find using MC using A and B. We know system, we know the system x dot equal to 1, 0, minus 1 xt plus 1, 0 ut. This is our A, this is our B. We can find, we know A. This is B. Oh, sorry, this is B. First part B, second part B, A square, A square. First. We can find, we know B. We can find AB. AB times minus 2, B 0. This is our AB. This is 2 by 1 meter. So this should be 2 by 1. Then M is to 2 by 2 meter. This should be rectangular. So we don't need A square B part. Here. We can write MC. MC B part first 0, 1, second part minus 2, 0. The theory is that this MC should be full rank. Square means it should be, I don't know, rectangular or square. I don't know how to say it. How much approach? Their number of rows should be equal to number of columns. As I think, as I, according to my understanding, this should be 2 by 2 meter. This is 2 by 1, so this should be 2 by 2 meter. Then this MC should be non-singular. We can say the determinant of MC equals 0. This is singular. Singular means this is uncontrollable. Uncontrollable means it should be unstable. We can't make the system stable using control. So it is unstable. This is the way we can say rank. This MC should be full rank. The rank of this MC equal 1. This is one row, so rank 1. Rank equal to 1. It is the full rank is 2. Number of rows 2. So this should be uncontrollable. So this is a non-singular. Actually, this part, non-singular system can be controllable. Two examples in the lectures. Other what is observability. Observability means we develop some system, we measure some output, and we can control system. But if we want, is it necessary to measure every output? Is it necessary to measure every output? No, some output can be fine. It can be found by other output, like if we measure angular angle theta, we can say we can use this theta to find theta dot. Right? Sort of relationship. We can use relationship, their relationship to find other output. That is observability. We can observe other output using one thing, one node to other output. We measure not everyone, we measure some special output. So then we can find other output. That's the yes. So that's the meaning of this observability. So we can find observability function, or we can say use some other theory also about this observability. But we can normally develop observability matrix. This is CA square like matrix. C means the output. Y should be equal to C times XT. This is the our control output. This is our final output. We develop our output using XT. XT and UT are represent system. They are system variables. XT is also system variable. This C could be a matrix, but it is a constant matrix. Output, final output, some constant times, some constant matrix times XT. This is okay. This is C. We can find C and we can find A. Then we can develop CA square, CA cube. Oh, right. This should be also a rectangular matrix. Here also rank, we can find the rank. But rank, this should be full rank. Okay, full stable, full stability. This should be full rank. Full rank. Or we can say this should be non-single. Non-single. Otherwise, we can say determinant of m not equal to state. We can find develop this matrix and say is the check the rank and say this is uh, observable system or this is not an observable system. Just example -2 0 0 -1 equal 1 0 comma. We
And
can
somebody,
find
yeah, in the questions, will they give the C matrix or we have to find?
most of the time they should give. Okay, we otherwise we can't say this is our C. Or we can say y equal xt, but how we can't say it should be given.
Right.
As I we can find C. C equals C. That's right. P -2 1 0. We can develop in first row C, second row C A -2 0. This is also non-singular, but here we need to check for column. First time above part for controllability we check row, rank of row. Here we need to check rank of column. So we can say determinant, check determinant m not 0, which is singular. Singular means this is unobservable. Observable system. Unobservable means we need to measure every single output. Okay. To feedback, we use feedback. This is feedback. So for this feedback, we need to measure every output. We need to measure. So we need number of, this is like xt per x1, x2, x3, like 3 by 1 matrix. There should be 3 sensors. Sensors for each state variable to find each state, each and every state. That's the meaning. Otherwise, it's if it is observable, only we need 1 or 2 sensors to say every output. Say xt to measure or observe x matrix. That's the brief idea. Sorry for the language mistake. I don't know actually AC part. You tell some part no.
Yeah, yeah. It's a
I don't. Fiction of AC part. I don't know about that. Welcome. So may I leave? I need to find some food for.
yeah, yeah, yeah. Thank you so much. Yeah. Super excellent. Yeah.